hidden over 10 billion light-years away, lies TON 618, the most massive black hole ever discovered. Its gravity can swallow entire galaxies, yet we barely understand how it formed. Tonight, we'll journey into its depths and explore the edge of what's known. If you enjoy this, please like, subscribe and share, and tell us in the comments, what would you ask if you could look inside a black hole? Thank you for watching. Now, let's begin. TON 618 lies within a universe so vast that its scale almost escapes comprehension. The observable cosmos extends for tens of billions of light-years in every direction, filled with countless galaxies grouped into immense filaments and clusters that thread through empty voids. From the nearest stars of the Milky Way to the faintest smudges detected by space telescopes, light defines the shape of everything that can be known. Across this immensity, the energy emitted by quasars like TON 618 becomes a marker of the early epochs when matter and gravity sculpted the first great structures. In the calm silence of spacelight, travels for eons, crossing the gulf between eras, carrying the record of how the universe once was. The observable universe is not uniform. Galaxies are arranged in a pattern resembling a cosmic web, with intersections where dark matter and gas collect. Within those dense nodes, supermassive black holes grow as galaxies form around them. They feed on gas and dust, drawn inward by gravity, converting a portion of that material into radiation so brilliant that it outshines the combined starlight of entire galaxies. These are quasars, luminous centers of galactic nuclei that reveal the most powerful engines known to physics. Among this population, some are faint and distant, others are bright and near, but only a few reach the extreme radiance and mass attributed to the object called TON 618. The light from this quasar began its journey roughly 11 billion years ago, when the universe was young, only a fraction of its current age. It moved through expanding space, redshifted as the cosmos stretched, shifting its wavelengths toward the longer, cooler part of the spectrum. This redshift, measured at around 2.2, allows astronomers to place TON 618 within a distant epoch where galaxy formation was vigorous and the supply of gas abundant. Each photon reaching Earth today has traveled through that deep time, bearing the imprint of matter shaped by gravity and radiation at cosmic dawn. The scale of such distances transforms familiar ideas of size and duration. A light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. Multiply that by billions, and even the smallest angular patch of the sky can hold innumerable galaxies. Instruments such as the Hubble Space Telescope and the more recent James Webb Space Telescope have extended our reach into this immensity, capturing images of galaxies whose light has been traveling since before the Milky Way existed. Within these observations lie the signatures of quasars like TON 618, their spectra recorded as thin lines dispersed through the light. They emit each line a code, revealing motion composition and temperature. The observable universe is also a record of time itself. Looking farther means looking backward. Every bright point visible through a telescope is a relic of an earlier era. The faint glow of the cosmic microwave background, the afterglow of the Big Bang, forms a distant horizon beyond which no light from the past can reach us. Between that primordial surface and the present moment stretch the histories of galaxies and black holes, each one a chapter in cosmic evolution. Within this continuum, the existence of objects like TON 618 demonstrates that enormous black holes already existed less than 3 billion years after the Big Bang. How they formed so quickly remains one of the profound questions in astrophysics. When astronomers map the large-scale structure of the cosmos, they identify clusters and superclusters linked by filaments of gas and dark matter. At the nodes of these networks lie quasars whose light pierces through intervening hydrogen clouds, leaving absorption features in their spectra. By studying such features, scientists trace the density and composition of intergalactic space. The presence of Ton 618 within this structure helps to anchor the distant scale of the universe, marking one of the most powerful sources known in the direction of the constellation Canes Venatici. Its brightness in the ultraviolet and optical range makes it an exceptional reference point for studying high redshift phenomena. The radiance of a quasar is not constant. It flickers sometimes subtly, sometimes dramatically, as the flow of gas into the central region changes. Over human timescales, these variations may appear slow, but on cosmic scales, they trace the rhythm of accretion and feedback, the exchange of matter and energy between a black hole and its host galaxy. Even at billions of light years away, instruments on Earth can detect such fluctuations. Through them, astronomers infer the structure of the surrounding material and the scale of the gravitational field. Ton 618's steady luminosity across decades of observation marks it as a stable but immensely powerful nucleus, a furnace of radiation in the deep past. The universe that contains such an object is governed by both simplicity and complexity. The basic laws, gravity, electromagnetism, and the behavior of matter under extreme conditions apply everywhere. Yet the outcomes differ vastly, depending on density, rotation, and time. From the quiet glow of nearby stars to the violent brilliance of quasars, all are expressions of the same fundamental physics. Ton 618 represents the farthest reach of those principles, an extreme where mass and energy approach the limits of what can exist without collapsing entirely. It is both a product of the universe's evolution and a participant in shaping it, returning energy to intergalactic space through jets and radiation that influence the formation of surrounding galaxies. From the vantage point of Earth, the light from Ton 618 is faint, requiring powerful telescopes and sensitive instruments to discern. Yet its signal carries across the cosmic ocean with remarkable clarity. Each detected photon contributes to a composite image, a spectral fingerprint that reveals the composition of the gas swirling around it. When assembled, those faint threads of data recreate a picture of an object so luminous that it once rivaled entire clusters of galaxies in output. That such light now arrives as a whisper underscores the scale of cosmic expansion where distance dims even the most brilliant beacons. The observable universe, then, is not a uniform field of light, but a layered record of transformation. Galaxies form, merge and fade, stars are born and extinguished, black holes consume and radiate. Among these billions of processes, the signal from Ton 618 remains one of the most remarkable, a steady point in a vast and changing sky. Its light, captured after traveling across most of cosmic history, invites the mind to follow it backward to the time when the first great structures of the universe were still emerging from primordial darkness. In tracing that journey, the story of Ton 618 becomes inseparable from the story of the cosmos itself, one luminous thread woven through the grand design of existence. Ton 618 belongs to an age when quasars illuminated the young universe with an intensity rarely seen today. Several billion years after the Big Bang, galaxies were rich in cold gas stars formed rapidly, and central black holes grew at extraordinary rates. Across that distant epoch, light from millions of active nuclei poured into space, giving rise to what astronomers call the quasar era. The night sky then, if seen from any nearby world, would have glowed with faintly bluish radiance, each pinpoint a beacon of accretion energy released as matter spiraled into a gravitational abyss. In that landscape of fierce activity, TON 618 stood among the brightest, a source whose power travelled across cosmic time to reach the present as a mere trace of its former brilliance. A quasar, or quasi-stellar object, appears star-like in ordinary telescopes, but reveals its true nature through spectra. The light is not from stars, but from gas heated to tens of thousands of degrees as it falls toward a supermassive black hole. This process converts gravitational energy into radiation with remarkable efficiency, producing luminosities hundreds of times greater than entire galaxies. During the quasar era, the universe was filled with such engines, each one anchored at the heart of a growing galaxy. Their collective output bathed intergalactic space in ultraviolet light, ionizing hydrogen left neutral after the first expansion of the cosmos. Through these luminous episodes, black holes and galaxies evolved together, shaping the large-scale structure still visible today. The era itself extended from roughly 10 to 12 billion years ago, corresponding to redshifts between about 1.5 and 3. At those distances, the light of quasars reaches us, stretched and softened by cosmic expansion. Each spectral line becomes a clue to both velocity and composition. Hydrogen, carbon, magnesium, and iron leave characteristic imprints in the light that crosses intergalactic space. For TON 618, those lines reveal gas moving at immense speeds under extreme gravitational influence. From these patterns, astronomers can measure not only distance, but the physical processes at work near its core. In every quasar, the same basic architecture repeats: a central black hole, an accretion disk surrounding gas clouds, and often a pair of jets. Yet the scale of TON 618 exceeds nearly all others, turning a familiar structure into something exceptional. In the early universe, fuel was plentiful. Vast reservoirs of hydrogen and helium filled young galaxies, feeding central black holes that had begun as remnants of the first massive stars, or as the direct collapse of enormous gas clouds. As they accreted matter, they emitted light heat and radiation pressure that pushed back against further infall, creating a cycle of growth and regulation. This balance between feeding and feedback determined how bright a quasar could become and for how long it could shine. In most galaxies, that phase lasted only a few tens of millions of years before gas supplies dwindled or were expelled. TON 618 represents one of those rare moments when conditions aligned to produce sustained and extraordinary activity. The quasar era marked a turning point for cosmic history. Before it, the universe was dominated by star formation. Afterward, it entered a more mature stage where large galaxies stabilized and their central black holes became quiescent. The intense radiation from quasars altered their surroundings, ionizing intergalactic hydrogen and contributing to the thermal evolution of the cosmic web. Light from this period still filters through intergalactic clouds, leaving delicate absorption features known as the Lyman alpha forest in the spectra of distant objects. TON 618's light carries that record, showing not only its own emission, but also the shadows of everything it passed along the way. In this sense, each quasar is both a lamp and a mirror, illuminating itself while reflecting the nature of the universe it inhabits. During this luminous epoch, black holes may have grown by both steady accretion and the merging of galaxies. When galaxies collided, their central black holes spiraled toward one another, forming even larger systems surrounded by turbulent flows of gas. The gravitational energy released in those mergers could drive bursts of radiation visible across vast distances. Observations of quasars like TON 618 provide evidence for such growth, revealing the cosmic mechanisms by which the most massive black holes attained their size. The discovery that quasars were not isolated anomalies but a common stage of galactic life transformed astronomy in the 20th century. The quasar population has since faded. Today, the nearby universe contains only a few active nuclei of comparable brightness, each much less luminous than its ancient predecessors. As galaxies aged and their gas supplies diminished, the engines at their cores quieted. TON 618, however, shines from a time when activity was at its peak, offering a window into an age now gone. Its light, stretched and thinned by expansion, allows astronomers to study the physical conditions that once prevailed throughout much of the cosmos. Through it, one can glimpse how energy, matter, and gravity interacted to create the structures seen around us today. To understand the importance of that era, consider the balance of radiation and gravity. The immense output of a quasar is powered by matter falling inward, yet that same radiation exerts outward pressure that can halt the infall if it becomes too strong. This limit, known as the Eddington limit, defines how bright a black hole can be for a given mass. TON 618's estimated brightness approaches that limit, suggesting it was accreting near the maximum rate allowed by physics. In that state, even a small increase in mass could dramatically alter the surrounding flow of gas, leading to bursts of variability that echo across space. The quasar thus represents a delicate equilibrium between forces that both create and restrain. The light we see today carries the memory of that equilibrium. It has traveled across an expanding cosmos, through clusters of galaxies and rivers of hydrogen, past countless other sources now long extinguished. Each photon arrives after a journey measured not in distance alone, but in the passage of cosmic time. When those photons reach the mirrors of a telescope, they complete a story begun billions of years before Earth existed. TON 618, as one of the brightest of these ancient objects, becomes a message from that energetic youth of the universe, encoded in wavelength and intensity. The era of quasars may seem remote, yet it defines much of what we observe today. The heavy elements forged in early stars, the large-scale distribution of galaxies, and the quiet centers of mature systems all trace their heritage to that time. When astronomers study TON 618, they are not only examining a single source, but also revisiting an epoch when the cosmos was young, crowded with light, and restless with creation. The quasar era ended billions of years ago, but its radiation still reaches us, shimmering faintly through the depths of space. In its persistence, the light of TON 618 remains both a relic and a guide, a steady signal from the age when black holes ruled the sky. TON 618 first enters the story of astronomy not as a blazing image in a telescope, but as a faint, anonymous entry in a catalogue. In the mid-20th century, when photographic plates were used to chart the ultraviolet sky, a small blue point was recorded among thousands of others. Its coordinates and brightness were noted, then set aside. Only later did detailed spectra reveal that this distant object was not a star at all, but a quasar, an active galactic nucleus shining from a time when the universe was young. The discovery unfolded slowly, built through data persistence and the gradual refinement of instruments capable of deciphering the light of the distant past. In the early 1960s, astronomers had just begun to recognize the existence of quasars. Objects such as 3C273 and 3C48 showed strange broad emission lines displaced toward the red, implying recession speeds that placed them billions of light-years away. The energy required to make such points of light visible across that distance was staggering. When the spectrum of this particular source was analyzed, its redshift of roughly 2.2 placed it even farther back in time, at a moment when galaxies were still forming their first massive structures. The light recorded on film represented radiation emitted 11 billion years earlier, an echo from an age of extreme cosmic activity. At the time, astronomical technique was as much craftsmanship as science. Researchers compared plates by hand, searching for faint variations in color or brightness that might reveal something unusual. Spectra were measured line by line, their wavelengths calculated manually and plotted on graph paper. The strange displacement of the lines in this quasar's spectrum indicated expansion on a cosmic scale, confirming that the object belonged to a remote epoch of the universe. The finding demonstrated how data patience and the interpretation of faint light could uncover something immense hidden within a single dot on glass. Radio observations soon followed. Sensitive receivers detected emissions suggesting jets of charged particles moving at relativistic speeds, interacting with magnetic fields far from the galaxy's center. The combination of optical and radio data revealed an active nucleus of exceptional power, one that converted gravitational energy into radiation with almost unimaginable efficiency. Through such cross-checks between different wavelengths, astronomers pieced together the anatomy of quasars, a supermassive black hole, an accretion disk, and vast flows of gas shaped by gravity and magnetic fields. This particular source, though only one among many, quickly proved remarkable for the sheer intensity of its light. As technology advanced, the picture sharpened. Improved telescopes and more sensitive detectors allowed astronomers to refine redshift measurements, examine the shape of emission lines, and estimate the mass of the central black hole. Even with conservative models, the inferred mass reached tens of billions of solar masses, placing it among the most massive known objects of its kind. The precision of these estimates remains limited, yet their consistency across different methods leaves little doubt that the nucleus of this quasar lies at the extreme frontier of what nature permits. Its energy output surpasses the collective radiance of entire clusters of galaxies, all concentrated within a volume smaller than the solar system. The significance of that discovery extends beyond scale. It offers a key to understanding how galaxies and black holes evolved together during the first few billion years after the Big Bang. Observations suggest that when a central black hole grows, its host galaxy grows as well, the two locked in feedback that regulates star formation and galactic structure. In that relationship, luminous quasars like this one represent the most intense phase of coevolution, a brief, brilliant moment when matter falls inward and light floods outward in balance. Studying such sources helps scientists reconstruct how modern galaxies reach their present form. Behind this progress lies the slow accumulation of measurements gathered by generations of instruments. The object catalogued decades ago now appears in multiple surveys, optical, infrared, and radio, each contributing details that refine the understanding of its nature. The Sloan Digital Sky Survey, the Very Large Telescope, and space-based observatories have all recorded its spectrum. Each new observation confirms its status as one of the most powerful known quasars. In the process, the source has become a benchmark for calibrating methods of measuring distance, luminosity, and mass at cosmological scales. What began as a faint notation on a photographic plate has become a cornerstone in the study of extreme astrophysical phenomena. The discovery also illustrates how the act of observing connects vastly different moments in time. The photons that formed the original images began their journey when the universe's first galaxies were still assembling. They traveled through cosmic expansion, through filaments of hydrogen, through billions of years of change, until finally striking the emulsion of a glass plate. In that instant, ancient light met modern curiosity, collapsing an immense gulf of time. Every observation since has been a continuation of that encounter, refining human understanding of a signal that has crossed nearly the entire history of the cosmos. Among the many quasars now known, this one remains distinctive, not only for its power, but for what it reveals about the early universe. Its existence demonstrates that enormous black holes could form rapidly, reaching billions of solar masses within only a few billion years after the Big Bang. How such rapid growth occurred remains an open question. Possible pathways include direct collapse of massive gas clouds, repeated mergers of smaller black holes, or sustained high-rate accretion lasting tens of millions of years. Each scenario challenges current models and pushes the limits of known physics. The quasar thus serves as both an observation and a mystery, a luminous clue to processes that shaped the structure of everything that followed. The recognition of its significance did not happen in a single moment, but through decades of quiet verification. Scientists re-examined the data-tested models and compared results, each step strengthening confidence in the measurements. In this way, the object became not only a subject of study, but also a measure of scientific patience. Its light continues to reach us unchanged while our tools and understanding evolve around it. The story of its discovery from an overlooked speck to a symbol of cosmic immensity reflects the nature of astronomy itself, an endeavor that transforms distant light into knowledge, linking the precision of instruments with the vastness of the sky. TON 618 endures in that record, not just as a number, but as a presence, a reminder that the quietest points on a photograph can conceal the loudest stories of the universe. Its detection marked the beginning of our awareness of one of the most massive black holes ever found, and its continuing observation connects generations of inquiry. From the early days of glass plates to the digital arrays of today, it remains the same ancient beacon, unchanged in its distant realm, yet constantly renewed through human discovery. The distance to a quasar, such as TON 618, cannot be measured by any direct means. It lies far beyond the reach of parallax, beyond standard candles, beyond every familiar scale of depth that astronomy once relied upon. Its remoteness must be inferred through the stretching of its own light. When radiation leaves a distant source, the expansion of the universe elongates its wavelength, shifting it toward the red end of the spectrum. This effect, called redshift, serves as both a measure of distance and a marker of cosmic time. By comparing the observed spectral lines of known elements with their laboratory counterparts, astronomers determine how much space has stretched during the light's journey. For this quasar, that redshift measures about 2.2, meaning the photons began traveling across the universe more than 10 billion years ago, when galaxies were only beginning to mature. The process of measuring light across such a distance is as intricate as it is revealing. A quasar's spectrum contains a pattern of emission lines, each one produced by specific atoms excited in the gas around the central black hole. Hydrogen emits a series of lines known as the Balmer sequence, while carbon, magnesium, and iron leave their own signatures. When observed through a spectrograph, these lines appear displaced, their wavelengths stretched by the expansion of space. The magnitude of this displacement provides a cosmic scale factor. The larger the redshift, the farther and older the source. In the case of this distant nucleus, the shift is extreme, a sign that we are seeing it as it was when the universe was less than a quarter of its current age. Determining the exact distance involves translating redshift into physical measurement. Cosmology provides the link through the expansion rate of the universe expressed by the Hubble constant. As the value of that constant has been refined through decades of observation, so too have the inferred distances to quasars. Modern measurements place this one roughly 10 to 11 billion light-years away in terms of light travel time, though its current proper distance accounting for continuing expansion may be more than twice that. The numbers themselves are immense, but what they represent is even greater a view of the cosmos at a time when its large-scale structures were still forming. Light from such a remote epoch does more than reveal distance. It carries within it the fingerprints of everything it encountered. As it travels, it passes through clouds of hydrogen gas scattered across intergalactic space. Each cloud absorbs specific wavelengths, creating a forest of narrow absorption lines superimposed on the quasar's own emission. This pattern, called the Lyman alpha forest, maps the distribution of matter between galaxies. The spectrum of this quasar, dense with these fine shadows, tells astronomers how the universe was structured billions of years ago. It is not only a record of one source, but of the entire cosmic web through which its light has travelled. Measuring brightness adds another layer of insight. The apparent magnitude of the quasar, as seen from Earth, must be corrected for distance and cosmic dimming to estimate its intrinsic luminosity. That correction reveals a power output thousands of times greater than that of an ordinary galaxy. Even accounting for the energy lost to distance and absorption, the energy emitted at the source is extraordinary. This luminosity is what makes quasars visible across such vast stretches of space. They are cosmic lighthouses, marking the locations of the universe's earliest active black holes. The object in question radiates across the electromagnetic spectrum from radio waves to ultraviolet and in some cases into X-rays, each band carrying clues to a different region of its structure. The act of measuring faint light from billions of years away demands precision of an almost poetic kind. Astronomers collect photons one by one, often over many nights, combining them into spectra where the faintest trace can alter a conclusion. Atmospheric turbulence must be corrected, instrumental sensitivity calibrated, and background noise removed. Even with all these refinements, uncertainty remains, yet the pattern of lines persists clearly enough to leave no doubt about the quasar's distance and nature. Its light, thin as it is, still carries the full geometry of its origin and the story of the space it crossed. Light serves as both messenger and chronicle. Every photon that arrives at a telescope mirror has travelled unimpeded since the moment of emission, crossing expanding voids where no matter exists to block its path. Along the way, the stretching of space has converted high-energy ultraviolet light into the visible and infrared ranges we can now detect. By analyzing this transformation, scientists reconstruct the history of cosmic expansion itself. In a sense, the light from this single source becomes a timeline of the universe, encapsulating billions of years in a single continuous beam. The colors of that light hold further information. Quasars emit most strongly in the ultraviolet, where gas near the black hole reaches tens of thousands of degrees. But by the time that radiation reaches Earth, it has been redshifted into visible wavelengths. The deep blues and violets have become pale golds and faint reds, their original intensity subdued by distance and time. This transformation turns the quasar into both a lamp and a clock. Its color tells how far its light has traveled, and thus how long the universe has been expanding. Each observation refines the measurement, improving models of cosmic evolution and the rate at which the fabric of space grows. The precision achieved in such work depends on comparison. Astronomers use known standards, hydrogen lines, galaxy clustering, and the cosmic microwave background to calibrate their distance scale. When the spectrum of this quasar is matched against those references, it fits neatly into the high redshift regime where the universe was dense, bright, and full of forming stars. Its measurement thus serves as a fixed point in the map of cosmic time. When plotted alongside others, it helps to outline the timeline of structure formation, showing how the early cosmos transitioned from chaos to order. These measurements also illustrate the remarkable consistency of physical laws. The same atomic transitions observed in a laboratory on Earth occur in gas clouds billions of light years away. The same quantum processes governed by the same constants produce identical spectral fingerprints. The fact that these distant lines match local ones confirms that the fundamental laws of nature have remained stable for most of cosmic history. In this way, a spectrum from a quasar is not only an astronomical observation, but a test of universal constancy. The atoms near a black hole in the distant past behave like the atoms here and now, linking everything in one continuum of physics. From the first detection to the modern era, every refinement in measurement has deepened the sense of scale. The redshift reveals when the light began its journey, the absorption lines describe the matter it encountered, and the luminosity indicates the power of the engine that produced it. Together they form a chain of reasoning that stretches from the smallest quanta of light to the largest expanses of space. The distance to the quasar is not merely a number, it is a bridge across time. Its light connects our present to an epoch when galaxies were newborn, and the cosmos was still writing the patterns that would one day shape us. Through these methods, astronomers have turned faint light into a precise language. Every wavelength speaks of velocity, temperature, and density. Every shift tells how the universe itself has changed. From such analysis emerges not only the scale of one extraordinary object, but the architecture of the cosmos as a whole. The act of measuring distance and light transforms remote radiation into knowledge, a conversion of brightness into understanding. Across 11 billion years, the photons that left that distant nucleus still whisper their message steady and unchanged, carrying both the evidence of their source and the enduring symmetry of the universe that sent them forth. Determining the mass of a black hole so remote and luminous as TON 618 requires methods that depend entirely on light. No spacecraft can ever reach it, and no nearby stars can be seen orbiting to provide the kind of gravitational measurement used in the Milky Way's center. Instead, astronomers rely on the behavior of gas close to the invisible core. As material spirals inward, it emits radiation and spectral lines, whose width reflects the speed of motion. The faster the gas moves, the stronger the gravity holding it, and from that velocity, one can infer mass. This principle, applied to the broad emission lines in the quasar's spectrum, provides the foundation for estimating the enormity of its central black hole. The region responsible for those lines is called the broad line region, a zone of dense high-velocity clouds orbiting near the accretion disk. Each cloud emits light that is shifted slightly in wavelength depending on its speed toward or away from us. The combined effect produces a broadened feature in the spectrum, sometimes spanning thousands of kilometers per second in velocity. By measuring the width of these lines and comparing them to the overall luminosity of the quasar, scientists can estimate the size of the region and, through the laws of motion, calculate the gravitational mass of the object that binds it. This method, though indirect, has become a cornerstone of extragalactic astronomy, allowing masses to be derived for objects far beyond any direct observation. In the case of this distant source, the lines of hydrogen and carbon appear extraordinarily wide, implying that the gas near its center moves at tremendous speeds. When the relationship between that velocity and the distance of the emitting clouds is applied, the resulting mass reaches tens of billions of solar masses. The numbers vary between analyses, some finding around 40 billion, others slightly less or more, depending on the scaling relations and assumptions about geometry. But all agree that the value lies at the extreme upper edge of known black holes, placing this nucleus among the most massive yet identified. Even the largest black holes at the centers of nearby giant galaxies rarely exceed a few billion solar masses, making this one a rare outlier in the cosmic population. Such estimates rely on calibration from closer systems where geometry can be mapped more precisely. In certain nearby active galaxies, astronomers measure time delays between variations in the central continuum and the response of emission lines, a technique known as reverberation mapping. These delays give the size of the broad line region, directly providing a scale that can then be extended to more distant quasars. For this high redshift object, such detailed mapping is impossible, but the established relationships allow a credible approximation. Though the margin of uncertainty may span a factor of several, even the lowest values imply a black hole of extraordinary proportions, one capable of shaping an entire galaxy through its gravitational reach. The challenge of understanding such mass lies not only in measuring it, but in explaining how it came to be. A black hole that massive existing less than 3 billion years after the Big Bang must have grown quickly. Normal accretion, limited by radiation pressure, would require longer than the available time, unless the seed black hole began enormous or fed at rates exceeding theoretical limits. Several models attempt to address this puzzle: the direct collapse of massive primordial gas clouds, the merger of multiple early black holes, or periods of super-Eddington accretion, when inflowing gas temporarily overwhelms outward radiation pressure. Each scenario suggests an environment dense and dynamic enough to build a colossus within the early universe's brief window. observational evidence from the quasar's brightness supports the notion that it accretes near the Eddington limit, where the inward pull of gravity balances the outward force of radiation. If it were any brighter, radiation would push material away faster than gravity could draw it in. If dimmer, it would not sustain its observed luminosity. This equilibrium defines a narrow band of stability that persists only as long as fresh gas continues to flow inward. The fact that the quasar remains luminous even now after billions of years of light travel time indicates that it once maintained that balance for an extended period. In that era, its central engine must have consumed enormous quantities of gas, converting a small fraction of mass into energy with astonishing efficiency. The mass estimate also depends on the inclination at which we view the system. If the broad-line region is flattened like a disk rather than spherical, and if our line of sight lies near its plane, the observed line widths may underestimate true velocities, and the actual mass could be higher. Conversely, if the system is seen face-on, velocities might appear larger than average, slightly inflating the calculation. Without direct imaging, the geometry remains uncertain. Even so, models constrained by other quasars suggest that orientation effects alone cannot explain away the sheer magnitude of this black hole's inferred mass. It is an authentic giant, not a trick of perspective. Additional checks come from the overall energy output. The luminosity of a quasar depends on the rate at which matter is converted to energy through accretion expressed as a fraction of the Eddington limit. By comparing observed luminosity with theoretical expectations for efficiency, usually around 10% of the rest mass of accreted material astronomers can estimate the mass required to sustain such brightness. These independent approaches converge on similar results, reinforcing confidence in the conclusion. The central black hole must weigh tens of billions of times more than the Sun, with a gravitational influence extending across hundreds of astronomical units. In a broader context, such measurements help define the population of ultramassive black holes. Each data point anchors models of cosmic growth, showing how mass is distributed among galaxies at different epochs. The relationship between black hole mass and stellar bulge mass observed in nearby galaxies implies that even this extreme object follows the same general trend, only scaled upward to monumental proportions. It suggests that its host galaxy, though invisible in current images, was itself enormous. A vast structure whose evolution was shaped by the outflows and radiation from its brilliant nucleus. The methods used to weigh distant black holes continue to evolve. Infrared and X-ray observations complement optical spectra, revealing different parts of the accretion process and helping to refine models of geometry and composition. Each refinement narrows the range of uncertainty, but the conclusion remains firm: the mass contained within that luminous center exceeds nearly all others measured. It represents the outer boundary of what gravitational collapse can produce under known physics. Whether this is a rare exception or the tip of a hidden population of equally massive objects is still unknown, but its existence sets a scale that theories of cosmic growth must now explain. Estimating such mass from faint red-shifted light demonstrates the power of inference in astronomy. From a handful of spectral lines and brightness measurements, the properties of an unseen object billions of light-years away can be deduced with remarkable precision. Each observation converts light into mass radiation, into gravity, and distance into knowledge. The result is both a measurement and a revelation, somewhere in the far reaches of the cosmos, a gravitational well of almost inconceivable depth once dominated its region of space. The number that defines its mass is not just a statistic, it is a measure of how far the human mind can extend through analysis and patience. The light that began its journey 11 billion years ago still carries that information faithfully, allowing those on a small world in the Milky Way to weigh one of the greatest engines the universe has ever produced. Every quasar, no matter how luminous, is part of a larger structure. The brilliance that reaches Earth is only the central glow of an entire galaxy hidden beneath the glare. Around the enormous black hole that defines this distant source lies a host galaxy whose light is overwhelmed by the nucleus, but whose presence is essential to its existence. It is the galaxy that supplies gas for accretion stars for gravitational structure and dark matter for stability. Though the host cannot yet be imaged directly, its properties can be inferred from the radiation it powers and the environment in which it resides. In that sense, to understand the quasar is to imagine the unseen system surrounding it, a structure vast enough to cradle one of the largest black holes ever known. The galaxy likely resembles a massive elliptical or bulge-dominated system, a form common among bright quasars. Such galaxies are ancient and spheroidal, their stars distributed smoothly rather than in spiraling arms. Their light is redder, composed mainly of older stars formed long before the quasar ignited. Observations of other high redshift quasars suggest that these hosts contain stellar masses of hundreds of billions of suns and are rich in gas that feeds both star formation and the central engine. The existence of a black hole weighing tens of billions of solar masses implies a host galaxy at least 1,000 times more massive, bound together by dark matter extending far beyond the visible edge. Within that vast halo gravity guides the slow dance of gas clouds, satellite galaxies, and intergalactic filaments, all contributing to the cosmic ecosystem of the quasar. The immediate environment around the host is shaped by both inflow and outflow. Gas from the intergalactic medium flows along cosmic filaments drawn toward the deep gravitational well of the galaxy. As it falls inward, it is heated, ionized, and sometimes compressed into new stars. At the same time, radiation from the active nucleus drives powerful winds outward, carrying matter back into space. These opposing flows create a dynamic balance regulating how much material reaches the center and how much escapes. The energy released by the accreting black hole thus influences not only its own growth, but also the evolution of the surrounding galaxy. This feedback mechanism is one of the central ideas in modern cosmology, linking the smallest and largest scales of structure. Around many quasars, faint extended halos of gas have been detected stretching hundreds of thousands of light years into space. These halos, known as circumgalactic media, act as reservoirs for future star formation and as archives of past activity. They glow softly in ultraviolet light illuminated by radiation from the nucleus. Though this distant quasar is too far for direct imaging of such detail, its spectral features suggest the presence of similar structures. Absorption lines in the quasar's light reveal clouds of ionized gas moving at various velocities, relative to the host, a sign of both inflowing material feeding the black hole and outflowing winds propelled by its energy. These patterns trace a circulation of matter that extends well beyond the visible galaxy, tying the quasar to the intergalactic environment around it. The region in which the galaxy resides is not isolated. At this redshift, The universe was densely populated with forming galaxies, many of them interacting or merging. Large-scale surveys show that quasars often appear at the centers of proto-clusters areas where dark matter and gas converge to form the seeds of future galaxy clusters. The intense radiation from a quasar can influence its neighbors, heating gas, suppressing star formation, or triggering it along the edges of expanding outflows. The host of this luminous nucleus may have lived in such a neighborhood surrounded by companions that shaped its history through gravitational tides and streams of shared matter. The presence of heavy elements in the quasar's spectrum gives further clues to its environment. Emission lines from carbon, nitrogen, and iron indicate that the gas near the nucleus has been enriched by previous generations of stars. Such enrichment could occur only if the host galaxy had already undergone several cycles of star birth and death before the quasar phase began. That finding implies a rapid and vigorous early history. Massive stars formed, exploded as supernovae, and seeded the surrounding gas with metals all within the first billion years after the Big Bang. By the time the quasar lit up, its host was already chemically mature, a sign of how quickly evolution proceeded in the early cosmos. The interaction between radiation and matter within this environment is continuous and profound. Jets emerging from near the black hole's poles can extend across interstellar space, colliding with gas clouds and compressing them into filaments that glow in radio and optical wavelengths. Shock waves propagate through the galaxy, shaping the distribution of gas, and sometimes triggering bursts of star formation far from the center. Even the outer halo, tenuously connected to the cosmic web, feels the influence of the central light as it ionizes hydrogen on scales larger than entire galaxies. In this way, the quasar acts both as an engine and as an artist, sculpting its surroundings with invisible hands of radiation and gravity. Though direct images of the host remain beyond current resolution, future telescopes are expected to change that. Instruments like the James Webb Space Telescope and the next generation of ground-based observatories can separate the glare of the nucleus from the faint glow of starlight around it. When that happens, astronomers will measure the size, shape, and star-forming history of the host directly. Such data will test models that link black hole growth to galaxy evolution. For now, the host of this quasar remains an inference described by light, but not yet seen existing in the mind's eye as a colossal elliptical galaxy veiled behind the brightness of its own heart. The environment beyond the host also contributes to its story. Along the line of sight, intervening galaxies and gas clouds imprint absorption features onto the quasar's spectrum. These marks reveal the presence of large-scale structures extending over millions of light-years. By studying these imprints, astronomers map the cosmic web itself using the quasar as a background lamp that silhouettes the universe. The same light that tells of the black hole's power also illuminates the vast expanse between galaxies, turning a single object into a probe of the cosmos. The scale of such an environment is difficult to grasp. Within a radius of several 100,000 light-years, the gravitational pull of the host galaxy holds stars' gas and dark matter in orbit. Beyond that, the influence fades, giving way to the larger gravitational fields of clusters and filaments. Yet even at those distances, the faint echo of the quasar's radiation continues to shape the ionization state of intergalactic gas. It is an influence that stretches far beyond the confines of a single galaxy, a reminder that no object in the cosmos truly stands alone. In contemplating this distant system, the mind must hold two images at once: the compact core where matter spirals into darkness, and the sprawling galactic body that surrounds it. One represents concentration, the other extension. Together, they form a single structure bound by gravity and linked through the exchange of energy and matter. The host galaxy and its environment are not mere background. They are the stage upon which the drama of the quasar unfolds the context that gives its radiance meaning. Even across billions of years, the faint patterns of its influence persist, written in the distribution of gas, the chemistry of stars, and the quiet glow of the intergalactic medium. Through these signs, the unseen galaxy that nurtured this distant nucleus continues to speak its voice, carried by light that has travelled since the dawn of cosmic history. Beyond the luminous body of the host galaxy, an immense and nearly invisible expanse surrounds the quasar, an ocean of rarefied gas known as the circumgalactic medium. It forms a transitional region between the galaxy and the wider intergalactic space, a zone where inflowing and outflowing matter meet, mix, and evolve. Though faint and difficult to detect, this vast envelope plays a crucial role in the life of every galaxy. It supplies the fuel that sustains star formation and receives the material driven outward by stellar winds and active nuclei. Around a quasar of this magnitude, the circumgalactic medium becomes an arena of extraordinary energy exchange, filled with gas heated, ionized, and stirred by the light and motion of the central engine. The existence of such halos was once speculative. For decades, astronomers suspected that galaxies were not isolated islands, but surrounded by vast reservoirs of gas extending for hundreds of thousands of light years. Only with the advent of sensitive spectroscopy and large telescopes did evidence emerge. By observing how the light of distant quasars passes through intervening galaxies, scientists detected absorption features revealing these extended atmospheres. In the case of an active quasar itself, its own light can illuminate the gas surrounding it, turning the circumgalactic medium into a faintly glowing cocoon, visible in ultraviolet and Lyman alpha emission. Although this particular source lies too far for detailed imaging, its spectrum carries the telltale signs of such a structure: broad absorption troughs, subtle shifts in line profiles, and the signature of ionized hydrogen distributed over immense scales. Within this region, temperature and density vary by orders of magnitude. Some clouds remain relatively cool at a few tens of thousands of degrees, while others are heated to millions of degrees by shocks and radiation. The gas is a mosaic of phases, neutral ionized molecular, constantly transformed by energy from the core. As radiation streams outward, it strips electrons from atoms, creating cascades of ionization that extend outward like invisible waves. Inward moving material drawn by gravity collides with these outflows, producing turbulence that stirs the halo. Each motion, each exchange contributes to the long-term evolution of the galaxy, regulating how matter cycles between the central regions and the cosmic web beyond. The circumgalactic medium acts as a buffer, absorbing the extremes of the quasar's power. When jets or winds emerge from near the black hole, they travel outward until their energy dissipates into this surrounding gas. Their shock fronts form compressing clouds and sometimes triggering localized regions of cooling that may later collapse into stars. At other times, the energy input is so strong that it drives material completely out of the system, enriching intergalactic space with heavy elements. Observations of similar quasars show halos containing metals like carbon and oxygen, evidence of prior generations of stars whose remnants have been cast into the larger environment. Through this exchange, the circumgalactic medium becomes both archive and laboratory, preserving the chemical history of its galaxy. Though the density of this gas is extraordinarily low, the total mass contained within the halo can rival that of all the stars in the galaxy combined. It represents a hidden component of the cosmic baryon budget matter that is not in stars dust or the interstellar medium, but in extended hot envelopes. By tracing absorption lines of hydrogen, silicon, and oxygen in quasar spectra, astronomers estimate that these halos contain a substantial fraction of the ordinary matter produced by the Big Bang. Around an object as powerful as this quasar, the balance between inflow and outflow determines how long such a reservoir can survive. If the outflows dominate the halo thins, quenching star formation in the host. If inflows prevail, fresh gas continues to feed both the galaxy and the accreting black hole. Models suggest that the circumgalactic medium around luminous quasars extends hundreds of thousands, perhaps even millions of light-years. In this vast domain, radiation pressure weakens with distance, but ionization remains significant. Photons from the quasar's ultraviolet continuum continue to excite hydrogen, far from the center, producing a faint haze of Lyman alpha emission. In nearby examples, long filaments of glowing gas have been observed surrounding active nuclei, tracing the paths of cosmic filaments that feed them. Although direct observation of such detail for this remote quasar remains beyond reach, its light shows that similar processes must occur there as well. The halo acts as both a recipient and transmitter of energy, carrying the influence of the central source outward into the larger universe. Within the halo, magnetic fields and turbulence shape the motion of gas. Small-scale eddies mix material of different temperatures, creating a complex structure rather than a uniform shell. Cosmic rays generated near the black hole propagate through this medium, adding another layer of interaction. Their presence may help drive outflows and maintain pressure balance within the gas. These interactions form a delicate system in which gravity, radiation, and magnetism compete for dominance. Over cosmic time, this balance determines whether the halo condenses to form new stars or disperses into intergalactic space. The circumgalactic medium also plays a key role in the visibility of the quasar itself. As light leaves the central region, it must pass through this layer of gas before escaping into the void. Scattering and absorption within the halo can alter the observed spectrum, changing both color and intensity. Variations in the thickness or composition of the gas can cause differences in brightness over time, contributing to the slow variability seen in some quasars. In this way, the halo not only surrounds the galaxy, but actively shapes the way it appears across cosmic distance. The dynamics of this region link directly to the cosmic web beyond. Filaments of intergalactic hydrogen feed into the halo, while energetic outflows from the galaxy inject heat and metals back into those same filaments. The result is a continuous exchange between galaxy and cosmos, a flow of matter that sustains the large-scale structure of the universe. Simulations show that such interactions are vital for explaining the observed distribution of galaxies, their masses, and their rates of star formation. The circumgalactic medium thus serves as a bridge between the small and the vast, connecting the internal life of a galaxy to the external architecture of the cosmos. Though this region cannot be seen with the naked eye, its presence can be imagined. Surrounding the quasar lies a diffuse, invisible sea of gas glowing faintly where radiation catches it, rippling where winds collide. It extends beyond any boundary of starlight, fading gradually into the intergalactic medium. Within that sea, atoms drift for millions of years before joining new structures. Each particle of hydrogen may one day become part of a star, a planet, or a being capable of wondering about its origins. The circumgalactic medium is not merely an astronomical feature. It is a reminder that creation and dispersal are continuous, that the energy radiating from one luminous point can echo across the entire history of the universe. The light that left this quasar billions of years ago still passes through such a medium, and in its spectrum, the traces of that journey remain, carrying evidence of the invisible ocean that once surrounded it, an ocean as wide as imagination and as calm as the silent depths of space. From the core of the quasar, narrow streams of matter erupt at nearly the speed of light, piercing through the galaxy and extending far into intergalactic space. These are relativistic jets, the most powerful outflows known in the universe. They originate near the event horizon, where magnetic fields twist and channel energy outward from the spinning black hole and the inner regions of the accretion disk. Though invisible to human eyes, they glow brightly in radio and X-ray wavelengths, marking the paths of particles accelerated to energies beyond anything produced on Earth. The presence of such jets transforms the surrounding environment, creating enormous lobes of radio emission that span millions of light years and leave a permanent imprint on the cosmic landscape. The formation of these jets depends on rotation and magnetism. As gas spirals inward through the accretion disk, it carries magnetic fields with it, winding them into tight coils around the black hole's axis. The rapid spin of the hole acts like a dynamo, converting gravitational energy into electromagnetic force. Under extreme conditions, that force can eject plasma along the poles, launching beams of electrons and positrons into space. These beams remain collimated by the surrounding magnetic field, and by the pressure of the disk itself, maintaining coherence across immense distances. Their creation is one of the most efficient energy conversion processes known, turning a fraction of infalling mass into kinetic power, capable of influencing regions far beyond the host galaxy. Observations of radio-loud quasars show that these jets can extend for hundreds of thousands, even millions of light years. At their termini, they inflate vast lobes of relativistic gas that glow in the radio spectrum. Each lobe marks the region where the jet's momentum dissipates into the intergalactic medium, heating it and mixing its contents. The energy involved is staggering, comparable to the total output of billions of stars sustained for millions of years. Although direct imaging of this quasar's lobes remains beyond current telescopic limits due to its distance, its radio spectrum reveals the same characteristic pattern: a steep decline in intensity with frequency, a signature of synchrotron radiation from charged particles spiraling through magnetic fields. These jets do more than illuminate space. They regulate the growth of their host galaxies. As they plow through interstellar and circumgalactic gas, they carve channels that can either trigger or suppress star formation. In some regions, the compression of gas along the jet's path induces bursts of stellar birth. In others, the heat and shock waves expel material, preventing new stars from forming. Over time, this feedback helps to balance the supply of cold gas, ensuring that the galaxy does not grow uncontrollably. For the most massive systems, Such feedback may be essential, explaining why galaxies of different sizes exhibit a consistent relationship between stellar mass and black hole mass. The quasar's jets act as cosmic regulators, maintaining equilibrium across scales that range from the subatomic to the intergalactic. The radiation from these jets spans the entire electromagnetic spectrum. In radio wavelengths, they appear as elongated lobes, in visible light as faint filaments, in X-rays and gamma rays as points of intense emission where shocks accelerate particles to near light speeds. The process responsible for this radiation, known as synchrotron emission, arises when electrons spiral through magnetic fields, losing energy as they radiate. Each photon produced carries information about the field strength, particle energy, and density of the medium through which it passes. By analyzing this radiation, astronomers reconstruct the physical conditions within the jets, tracing their evolution from compact cores near the black hole to diffuse lobes that stretch across intergalactic space. The symmetry of many radio quasars suggests that jets are launched in opposite directions, simultaneously aligned with the spin axis of the black hole. In some cases, only one jet appears visible because the other is directed away, its radiation diminished by relativistic effects. The beaming of light in the direction of motion causes the approaching jet to appear brighter and the receding one fainter. This phenomenon, called Doppler boosting, reveals the near-light speeds of the outflows. From such measurements, astronomers infer velocities exceeding 99% of the speed of light, confirming that these are among the most extreme natural accelerators in existence. The influence of these outflows extends well beyond the visible galaxy. When the jets encounter the surrounding medium, they transfer momentum and heat, stirring intergalactic gas and shaping the structure of the cosmic web. Observations of distant radio sources show cavities in the X-ray emitting plasma of galaxy clusters, evidence of energy injection from similar processes. Each jet acts as a conduit through which gravitational energy is returned to its environment, connecting the smallest scales of black hole physics to the largest scales of cosmic structure. The distant quasar serves as a testament to this feedback, demonstrating how a single compact object can affect regions spanning millions of light years. Inside the host galaxy, the jets interact with interstellar clouds, producing knots of emission and shocks that glow in optical and infrared light. These regions often trace the boundaries where the jet's plasma meets dense gas, forming bright filamentary structures. The dynamics are violent, yet they create patterns of remarkable beauty, arcs, rings, and wisps illuminated by radiation from the collision fronts. In the more extended lobes, the energy density drops, and the radiation fades slowly over millions of years, leaving behind relics of past activity. Even after the central engine quiets, these lobes continue to shine, faintly echoing the power that once sustained them. The physical mechanisms driving jet formation remain an active area of research. The most widely accepted model, the Blandford-Znajek process, describes how rotational energy from a spinning black hole can be extracted through magnetic fields anchored in the accretion disk. In this view, the black hole acts as a cosmic flywheel, converting spin into electromagnetic energy that launches the jets. Numerical simulations support this concept, showing how magnetic field lines twist and snap, releasing enormous amounts of energy. Yet details remain uncertain: the exact composition of the plasma, the efficiency of acceleration, and the stability of the flow are subjects of continuing investigation. Each discovery brings theory closer to matching the grandeur of what observation already reveals. In the early universe, when this quasar emitted its light, such jets were likely common. The high availability of cold gas, frequent galaxy mergers, and rapid black hole growth created perfect conditions for powerful outflows. Over cosmic time, as fuel diminished and galaxies matured, the frequency of these phenomena declined. Today, only a few active galaxies exhibit comparable behavior, reminders of an epoch when the cosmos was brighter and more turbulent. The light from this distant system thus captures not just one object's activity, but an entire era of energetic transformation. To imagine the scale of these structures is to stretch comprehension. From the tiny region near the event horizon, no larger than a solar system, streams emerge that travel for millions of years before fading. Their paths trace the influence of a single gravitational source across intergalactic space, binding together matter and energy in a continuous thread. Even now, after 11 billion years of expansion, the radiation from those jets reaches Earth, carrying with it the signature of ancient motion. They remind us that the energy released by gravity can shape the architecture of the cosmos itself, turning the fall of gas into light motion and form. In that light, the distant quasar endures as a silent architect of structure, its jets drawing invisible lines through the universe that remain long after their origin has faded from sight. Surrounding the distant quasar lies a faint extended veil of light known as a Lyman alpha nebula. This glowing structure, composed primarily of hydrogen gas, radiates in the ultraviolet line that marks the transition of electrons in the hydrogen atom's lowest energy state. When observed from Earth, that ultraviolet light, stretched by the expansion of space, appears in the visible range as a pale ghost-like halo around the quasar. Although almost imperceptible to ordinary vision, this nebula records the flow of gas between the galaxy, its circumgalactic medium, and the cosmic web beyond. It is a bridge between the internal life of the quasar's host and the vast intergalactic structures that feed it. Within this ethereal glow, matter and radiation engage in a continuous dialogue, shaping both the evolution of the galaxy and the surrounding universe. The origin of such nebulae lies in the interaction of radiation and hydrogen. As energetic photons escape from the quasar's core, they ionize the surrounding gas-stripping electrons from hydrogen atoms. When those electrons recombine, they emit photons at the characteristic Lyman alpha wavelength. The cumulative effect of countless such transitions creates an extended emission field visible over distances of hundreds of thousands of light years. In some quasars, the nebula takes on filamentary forms, tracing the channels through which gas flows toward the center. In others, it appears as a diffuse sphere of light, faint but immense. The pattern reflects the structure of the intergalactic medium itself, shaped by gravity turbulence and feedback from the central source. Detecting these faint emissions requires exceptional sensitivity. Using narrow band filters centered on the red-shifted Lyman alpha line, astronomers isolate the glow from the overwhelming brilliance of the nucleus. Observations of nearby analogues show vast sheets of hydrogen gas extending far beyond the visible galaxy, some reaching scales of several 100,000 light-years. Although this distant quasar is too remote for direct imaging at such resolution, its spectrum bears unmistakable signs of similar phenomena. The broad asymmetric profile of its Lyman alpha emission line indicates that radiation is being scattered and re-emitted by large volumes of gas surrounding the nucleus. This signature points to a nebula, both massive and active, a structure where photons and atoms interact across cosmic scales. The nebula serves as both record and participant in the cosmic cycle of matter. Streams of cold hydrogen flow inward along filaments of the cosmic web, feeding the galaxy and sustaining the accretion that powers the quasar. At the same time, intense radiation and winds from the nucleus drive gas outward, enriching the environment with heavier elements. The Lyman alpha glow arises where these opposing motions meet. It marks boundaries between inflow and outflow, between regions dominated by gravity and those ruled by radiation. In these zones, shocks and turbulence generate complex patterns of density and temperature, each leaving subtle imprints on the emitted light. By studying these patterns, astronomers reconstruct the geometry of the quasar's environment, turning faint lines into maps of motion and structure. The presence of heavy elements in the nebula indicates a history of stellar activity. Supernovae within the host galaxy have expelled metals into the halo, mixing them with primordial hydrogen. These elements modify the cooling behavior of the gas, allowing it to condense more efficiently and to radiate energy through additional spectral lines. As a result, the Lyman Alpha Nebula becomes more than a hydrogen cloud. It is a composite of enriched matter circulating between the galaxy and the cosmic web. In this interplay, the nebula embodies the universe's ongoing transformation. Simple atoms forged in the Big Bang, evolving into complex structures through cycles of light and gravity. The behavior of the nebula light reveals further subtleties. Because photons at the Lyman alpha wavelength interact strongly with hydrogen, they scatter many times before escaping, making the emission diffuse and extended. This scattering smears the image, producing a soft halo-like appearance rather than sharp boundaries. It also creates polarization patterns that can be measured to infer the direction of gas flows. In some quasars, these observations show outward motion consistent with winds driven by radiation pressure. In others, they suggest infall as gas streams toward the black hole's gravitational well. For this distant object, the balance likely involves both a complex circulation in which energy from the core drives material outward, even as cosmic gravity pulls new matter in. The nebula also acts as a tracer of the surrounding cosmic filaments. In deep images of similar systems, faint tendrils of Lyman alpha emission connect the quasar to neighboring galaxies, outlining the scaffolding of the cosmic web. These filaments carry cold gas that fuels both star formation and black hole growth. Where they intersect, clusters and superclusters eventually form. The light from such structures, seen as it was billions of years ago, reveals the framework of the young universe. By measuring the distribution of Lyman alpha emission around distant quasars, scientists can test models of large-scale structure formation and the role of feedback in shaping the intergalactic medium. At smaller scales, the nebula interacts directly with the quasar's outflows. High-velocity winds and jets penetrate the surrounding gas, compressing it into shells and filaments. These shocks enhance Lyman alpha emission, creating knots of brightness within the diffuse glow. Over time, such interactions may fragment the gas-producing clumps that later cool and collapse into new stars. In this way, the nebula serves as both byproduct and nursery, transforming the energy of the quasar into potential sites of creation. The process illustrates the constant exchange between destruction and renewal that characterizes cosmic evolution. The faint halo also provides a means to estimate the total gas content of the quasar's environment. By measuring the intensity and extent of the emission, astronomers calculate the mass of hydrogen present and the rate at which it moves. These estimates suggest reservoirs containing billions of solar masses of gas, sufficient to sustain both star formation and accretion for tens of millions of years. Such abundance helps explain how the central black hole achieved its enormous size in so short a cosmic time. The nebula, in essence, is the signature of the fuel supply that once maintained the quasar's brilliance. Viewed in context, the Lyman Alpha Nebula stands as a transition zone, a place where the local and the cosmic meet. It is neither purely galactic nor purely intergalactic, but a bridge through which matter and energy continuously flow. The photons that produce its glow are ancient messengers, tracing pathways of motion that link a single black hole to the entire fabric of the universe. When they reach Earth, redshifted and dimmed, they carry within them the record of that connection. Through them, the faint light of a hydrogen atom becomes a document of cosmic architecture. In imagination, one might picture this region not as a static cloud, but as a slow, silent motion filaments, drifting light, scattering energy, dissolving into distance. Each wisp of hydrogen reflects the interplay of forces that govern the cosmos: gravity drawing inward, radiation pushing outward, expansion stretching space itself. The Lyman Alpha Nebula surrounding the quasar is a portrait of that balance. Though faint and diffuse, it embodies the largest patterns of existence, showing how the simplest of atoms can reveal the deepest of structures. Its glow, having crossed billions of years, arrives now as a whisper of the universe's youth, carrying in its delicate light the memory of creation unfolding on a cosmic scale. Closer to the central engine than the vast nebula and halo lies a compact turbulent zone of gas known as the broad line region. It is here that the most distinctive features of a quasar's spectrum originate. Within this region, gas clouds orbit at extraordinary speeds, moving thousands of kilometers per second under the influence of the black hole's gravity. Each cloud glows as it absorbs intense radiation from the accretion disk and then re-emits that energy at specific wavelengths. Because of the immense velocities involved, those spectral lines are broadened into smooth, wide profiles rather than narrow spikes. This broadening, first noticed in the earliest quasar spectra, is what defines these objects as distinct from ordinary galaxies. The broad line region is both the visible signature of the quasar's activity and one of the most important clues to the physical processes occurring near the event horizon. The structure of this region is not directly observable even in the nearest quasars, but models based on spectroscopy and reverberation mapping provide a consistent picture. The gas is arranged in a roughly spherical or flattened distribution extending from light days to light months around the black hole. Each cloud or filament is ionized by ultraviolet and X-ray radiation from the inner disk, producing emission lines of hydrogen, carbon, nitrogen, and oxygen. The diversity of these lines reveals a complex environment with multiple temperatures and densities coexisting in equilibrium. Some zones are dominated by high ionization species glowing in ultraviolet, while others emit in optical wavelengths. Together they create a spectral fingerprint that identifies the quasar across cosmic time. In the case of a luminous source like this one, The velocities in the broad line region are immense. Measurements of the hydrogen Balmer lines suggest motion of several thousand kilometers per second, while higher ionization lines indicate even faster speeds. These values correspond to orbital distances only a few light weeks from the central black hole regions, where gravity warps both space and time. Light emitted from one side of the region is redshifted by the gravitational field, while light from the opposite side is blue-shifted as gas approaches along its orbit. The resulting blend produces the characteristic broad asymmetric shapes seen in spectra. By analyzing these profiles, astronomers extract estimates of mass density and dynamics using light itself as a probe of invisible motion. The broad line region does not remain static. It responds to changes in the central continuum, brightening or fading as the energy output of the accretion disk varies. This reprocessing occurs with measurable time delays, typically days to weeks, corresponding to the light travel distance between the disk and the emitting gas. Monitoring these variations allows scientists to perform reverberation mapping, one of the few methods capable of measuring the size of structures so small and remote. For nearby active galaxies, this technique provides precise measurements of the region's radius and, by extension, the black hole's mass. Although the extraordinary distance of this quasar prevents such direct study, the same physical principles apply. Its spectrum, frozen in time, records the integrated behavior of these rapid processes. The conditions within the broad line region are extreme. Gas densities can reach billions of particles per cubic centimeter, temperatures climb to tens of thousands of degrees, and the radiation field is intense enough to ionize nearly every atom. Under such circumstances, clouds must be continually replenished. Some models suggest that the gas originates in the surface layers of the accretion disk, lifted by radiation pressure, and then falling back in a continuous fountain. Others propose that it arises from stellar winds within a dense cluster of stars orbiting close to the black hole. Whatever the mechanism, the result is a dynamic equilibrium in which inflow and outflow coexist, sustained by the balance of gravity, pressure, and light. The broad line region also provides a means to trace the composition of the gas. The relative strengths of different emission lines indicate chemical abundances, revealing that the material near the black hole is enriched with heavy elements. This enrichment implies a long history of star formation and supernova activity within the host galaxy prior to the quasar's ignition. The presence of metals such as iron and magnesium shows that multiple generations of stars had already lived and died, recycling their material into the interstellar medium. The quasar thus sits at the end of a long chain of cosmic evolution, its present radiance built on the legacy of earlier stars. Radiative transfer within this region is complex. Because the gas is dense and highly ionized, photons undergo countless scatterings before escaping. Each interaction modifies the line profile and alters the apparent velocity distribution. The result is a smooth continuum of motion that hides individual cloud structures. Some theories describe the region not as discrete clouds, but as a continuous wind emerging from the accretion disk, shaped by magnetic forces and radiation pressure. In that scenario, the broad lines are formed within the accelerating outflow itself, and their widths reflect the velocity gradient along the line of sight. Whether composed of clouds or wind, the region acts as a luminous veil through which the innermost light must pass. gravitational and relativistic effects near the black hole add further layers of complexity. Time dilation causes processes near the event horizon to appear slower to distant observers, while gravitational redshift shifts emitted light to longer wavelengths. These effects combine with orbital motion to sculpt the detailed shapes of emission lines. In the brightest quasars, such features can sometimes reveal hints of the accretion disk's inclination and rotation, offering indirect glimpses of the geometry near the core. The spectrum of this distant object, though blurred by distance, still carries those signatures in softened form, a record of light that has climbed out of a deep gravitational well to reach us. The broad line region also connects to other components of the quasar environment. Above it lies the corona, a zone of extremely hot plasma that emits X-rays and illuminates the gas below. Beyond it, dust and molecular gas absorb and re-radiate energy in infrared wavelengths. Together, these layers form a complex hierarchy of radiation and matter. Each region influences the others. X-rays from the corona alter the ionization state of the broad line clouds, while outflows from the disk carry material outward to feed the dusty torus. The system operates as a single interdependent structure, driven by gravity but moderated by light. In studying this region, astronomers learn not only about the distant quasar, but about the universal mechanisms of accretion and radiation. The same principles that govern these titanic systems also apply in miniature to black holes in nearby galaxies, and even to compact objects in binary stars. The broadline region is therefore a bridge between scales, demonstrating that the physics of the very large and the very small are linked by common laws. In the calm of deep time, the light from this zone travels outward, crossing the circumgalactic medium and intergalactic space before reaching Earth. It arrives as a spectrum, a pattern of brightness and color that, when decoded, tells of velocities, temperatures, and compositions unimaginable in our immediate world. The broadline region remains unseen, yet vividly present. In that light, its turbulent orbits captured in the spread of wavelengths, its temperature preserved in the strength of its lines. Through these signals, the hidden motion of gas near a distant black hole becomes visible across billions of years. The quasar's broad lines are more than features on a graph. They are echoes of gravity itself, stretched and softened by space and time, carrying the breath of a distant, restless core into the silence of the present cosmos. At the heart of every quasar lies a structure of staggering precision and violence, the accretion disk. This is the luminous engine that powers all the light, heat, and motion surrounding the central black hole. It forms as gas drawn by gravity settles into a flattened, rotating disk, spiraling inward through friction and magnetic turbulence. Each particle of matter loses energy as it collides with others, gradually moving closer to the center, where gravitational potential converts into radiant power. Around a black hole of tens of billions of solar masses, this disk stretches for light days, across, yet is only a fraction of that in thickness, a cosmic whirlpool glowing across the electromagnetic spectrum. It is from here that the quasar's light originates, the place where infalling matter becomes radiation before crossing the final threshold into darkness. The temperature within the disk changes smoothly from outer to inner regions. Far from the center, gas remains relatively cool, shining in infrared and optical wavelengths. Closer in, friction and compression heat the material to tens of thousands of degrees, producing ultraviolet radiation. Still nearer the event horizon, temperatures rise into the millions of degrees, generating X-rays and sometimes gamma rays. The result is a continuous spectrum extending across nearly all observable frequencies. The balance of these emissions reveals the structure of the disk itself. For an object as massive as this quasar, the peak output lies in the ultraviolet, where the combined light of countless hot zones merges into a smooth continuum of power. That continuum defines the quasar's apparent color, brightness, and energy distribution across space. The accretion disk operates under an extraordinary regime of physics. Gravity pulls matter inward, but angular momentum resists collapse. The competing forces create shear producing friction that converts motion into heat. Magnetic fields within the ionized gas twist and reconnect, driving turbulence that enhances this transport of angular momentum. This process, known as magneto-rotational instability, enables matter to drift inward, efficiently maintaining the flow that sustains the quasar's brilliance. Without it, gas would orbit indefinitely, and the engine would fade. With it, the black hole consumes matter at a steady pace, radiating energy with remarkable consistency. The radiative efficiency of such a system can reach up to 10% of the rest mass of the accreted material, far exceeding that of any known stellar process. The structure of the disk is thin, but not uniform. The inner regions rotate at relativistic speeds, where time dilation and frame dragging alter the paths of particles and photons. These relativistic effects distort the disk's appearance to a distant observer. One side moving toward us appears slightly brighter due to Doppler boosting, the other moving away appears dimmer. Light emitted near the inner edge bends around the black hole, forming a subtle ring of lensed radiation. In nearby active galaxies, these effects have been simulated and even observed in detail. But for this faraway quasar, they manifest only as integrated features within its spectrum, a blend of shifted and broadened lines that hint at the underlying motion. The innermost stable orbit marks the boundary between radiating gas and the plunging region where matter falls directly into the black hole. For a rotating black hole, this boundary can lie as close as a few gravitational radii. Inside it, time and space curve together, and the distinction between orbit and descent dissolves. As material approaches this region, its orbital velocity nears the speed of light, and the energy released per unit mass reaches its maximum. The radiation produced here dominates the quasar's luminosity, making the inner disk the most efficient energy source in the known universe. The light emitted from this frontier carries information about the spin of the black hole, since rotation determines how tightly the disk can orbit before crossing the horizon. Measuring subtle shifts in the high-energy spectrum allows astronomers to infer that many supermassive black holes, including this one, likely spin rapidly, preserving angular momentum from their formation. Above the disk hovers a tenuous region of hot plasma called the corona. It is the source of X-rays that scatter and reflect off the disk's surface, producing characteristic spectral features such as the iron K-alpha line. These interactions create echoes of the inner geometry, offering one of the few glimpses into the environment closest to the event horizon. Though the details remain uncertain, the corona may form through magnetic reconnection or turbulence, releasing bursts of high-energy radiation that fluctuate over time. In nearby quasars, such variations have been recorded as changes in brightness lasting hours or days. In this distant case, time dilation stretches those events across millennia, preserving them in the averaged glow we now see. The accretion disk also drives winds. As radiation escapes from the hot inner regions, it exerts pressure on the surrounding gas-lifting material away from the surface. These winds carry matter outward at thousands of kilometers per second, shaping the broad line region and feeding the larger-scale outflows that extend into the circumgalactic medium. Some of this material eventually returns, falling back in cycles that maintain the balance between inflow and feedback. This circulation of matter and energy regulates the growth of the black hole and determines how long the quasar remains active. When the supply of gas diminishes, the luminosity fades, the disk cools, and the galaxy returns to a quieter state. For the distant quasar, we observe it in full power, its disk still bright, its structure intact, and its energy reaching across 11 billion years of expansion. Observing such a disk directly is beyond current technology, but its presence is confirmed through its spectral fingerprint. The smooth continuum emission, punctuated by broad lines, arises from the temperature gradient of the disk. By fitting theoretical models to this shape, astronomers can estimate the rate at which matter falls inward and the efficiency of conversion to radiation. For this quasar, the implied accretion rate approaches the Eddington limit, meaning it shines at nearly the maximum luminosity that gravity can sustain. In that state, even small changes in mass or inflow can produce dramatic effects, yet the balance holds. The disk endures as a steady blazing sheet of plasma, transforming matter into light at the threshold between stability and collapse. The energy produced in the accretion disk extends its influence far beyond the immediate environment. Ultraviolet radiation ionizes the surrounding gas, powering emission lines in the broad line region. Radiation pressure drives galactic-scale winds. Magnetic fields anchored in the disk launch relativistic jets that pierce intergalactic space. The disk is thus the central link connecting all other components of the quasar's ecosystem. It is the origin of the light that illuminates the Lyman Alpha Nebula, the force that shapes the circumgalactic medium, and the catalyst for the chemical evolution of the host galaxy. Every photon emitted from the quasar's distant glow began its journey from the swirling surface of this structure. The physics of accretion disks unites theory and observation in a single elegant model. Equations describing angular momentum viscosity and radiation transport predict the same temperature profiles and luminosities that telescopes record. In this harmony between mathematics and light lies the profound beauty of astrophysics. The unseen motions of gas near a black hole can be understood through the patterns of color and brightness that reach Earth. For the great quasar in the distant universe, that understanding transforms faint light into a story of energy, balance, and motion. The accretion disk, invisible yet all-revealing, remains the heart of the quasar, an immense glowing plane of ordered chaos, spinning endlessly at the edge of time, turning gravity itself into the radiance that still crosses the dark to reach us now. Above the luminous surface of the accretion disk hovers a thin but extremely hot veil of plasma known as the corona. It is one of the most enigmatic features of a quasar, a realm where temperatures reach hundreds of millions of degrees, and where the familiar rules of light and motion begin to twist under the influence of gravity. The corona emits high-energy X-rays that interact with the cooler layers of the disk below, scattering and reflecting in patterns that encode the geometry of space near the black hole. These X-rays are among the last signals produced before matter disappears beyond the event horizon, carrying the imprint of conditions in a region where space-time is curved almost beyond recognition. The origin of the corona lies in magnetic turbulence. As the ionized gas of the disk churns under differential rotation, magnetic field lines become tangled and then reconnect, releasing bursts of energy that heat the plasma to extreme temperatures. This process, akin to the solar corona, but vastly more energetic, fills the space above the disk with a storm of high-energy electrons. When photons from the disk collide with these electrons, they are boosted to higher energies through a process called inverse Compton scattering, creating the X-ray continuum observed in quasar spectra. These photons then strike the disk again, producing fluorescent emission lines that reveal the composition and structure of the material. Among these, the iron K-alpha line stands out, distorted by the intense gravitational field into a broad, asymmetric shape. The corona's light does not travel freely. Near a black hole, gravity bends the paths of photons, curving them around the massive object and allowing some to circle it multiple times before escaping. This bending, known as gravitational lensing, enhances the brightness of certain regions of the disk while hiding others. The effect produces a distorted ring-like pattern that, if observed directly, would appear both familiar and alien, a luminous ellipse where time and geometry blur together. For distant observers, these distortions merge into subtle asymmetries in the spectrum detectable only through careful modeling. Yet within those details lies a record of the warped space-time surrounding the black hole. Relativity also alters the perception of time and color in this domain. Gas, orbiting near the inner edge of the disk, moves at significant fractions of the speed of light. To an external observer, time within this region appears to slow, and light emitted from the receding side of the disk is red-shifted, while that from the approaching side is blue-shifted. The combined effect smears spectral features into broad curves that carry the unmistakable signature of relativistic motion. These shifts, observed in X-ray and ultraviolet spectra, confirm that matter in the innermost disk moves under the direct influence of Einstein's equations rather than Newton's. Every photon that escapes from this region must climb out of a deep gravitational well, losing energy as it travels, its wavelength stretched by the warping of space itself. The interaction between the corona and the disk creates an intricate feedback system. X-rays from the corona heat the upper layers of the disk, altering their opacity and ionization state. In turn, the disk emits ultraviolet radiation that cools the corona and influences its density. This exchange establishes a delicate equilibrium that regulates the quasar's high-energy output. When the corona brightens, the disk's reflected emission strengthens. When it dims, the reflection fades. Observing these variations provides one of the few ways to map structures so small that they remain forever beyond direct resolution. In nearby active galaxies, light echo studies show that changes in X-ray brightness are followed by corresponding changes in the reflected light after brief time delays, revealing distances of mere light hours. For this distant quasar, the same processes unfold, stretched by cosmic expansion and time dilation until they blend into a steady radiance. Within the corona, conditions defy ordinary intuition. The plasma is nearly collisionless, with particles moving in complex magnetic loops that channel energy outward. Temperatures exceed those at the center of stars, yet the density is low, allowing radiation to escape freely. Electrons moving through the magnetic fields emit synchrotron radiation adding to the X-ray and gamma-ray continuum. The light produced here fluctuates chaotically as magnetic fields reconfigure, but over cosmic distances, these fluctuations merge into a smooth signal. Each photon that reaches Earth from this realm has undergone countless scatterings, carrying with it the memory of turbulence in one of the universe's most extreme environments. Relativistic effects extend beyond the corona itself. The curvature of space-time near the black hole causes photons traveling on slightly different paths to experience different gravitational potentials. This creates subtle delays and energy shifts that can be measured in principle as echoes in the light curve. By studying these echoes, astronomers attempt to reconstruct the three-dimensional geometry of the inner accretion flow. In the local universe, observations of such reverberation have begun to confirm theoretical predictions revealing compact coronas confined within only a few gravitational radii of the event horizon. Extrapolated to this luminous and distant quasar, the same geometry would encompass a region larger than the solar system, yet tiny compared with the surrounding galaxy, an island of intense radiation floating in the sea of curved space. The immense gravitational field also affects how energy escapes. Not all light produced near the black hole can reach the wider universe. Some photons fall back into the disk, others spiral inward and vanish. The fraction that escapes does so along curved trajectories, concentrating into narrow beams that define the apparent brightness of the quasar. These beams, shaped by relativistic motion, may explain why some quasars appear brighter when viewed from certain angles. The effect is not an illusion, but a fundamental consequence of motion and gravity combined. The light we see today is only a portion of what was emitted those photons fortunate enough to have followed paths that lead outward across billions of years. The corona also serves as the launching point for the quasar's jets. Magnetic fields anchored in the rotating disk thread through this plasma channeling angular momentum and energy along the poles. As the black hole spins, it drags space-time with it, twisting these field lines into helical structures that accelerate particles outward. The process links the smallest scales near the horizon with the largest structures in the cosmos, bridging distances of millions of light-years. Thus the corona, though confined to a region no larger than a few light days, influences phenomena that shape entire galaxies and beyond. The physics that govern these interactions rest upon the principles of general and special relativity. In the curved space near the black hole, energy, motion, and geometry become inseparable. Light follows the shape of gravity, and time flows differently depending on position. To study such regions is to confront the limits of observation, where concepts like inside and outside lose clear meaning. Yet through spectra and models, astronomers can describe these invisible realms with remarkable accuracy. Each measurement, each fit of data to theory, transforms abstract equations into a picture of the cosmos operating at its most extreme. The light that finally escapes from the corona and disk has traveled through layers of distortion, scattering, and gravitational bending before entering the expanding universe. Over 11 billion years, it has stretched into longer wavelengths, cooling and fading as it journeys through space. By the time it reaches modern detectors, it carries with it the compressed story of motion, heat, and relativity from a realm just beyond the brink of no return. To decode that light is to listen to the last words of matter, before silence, the quiet release of energy, where time slows, light bends, and gravity reigns supreme. It is a reminder that what we observe across cosmic distance is not only the power of a black hole, but the enduring precision of nature's laws, consistent from the smallest atom to the vastest abyss, preserved in every photon that finds its way across the darkness to us. At the very center of the quasar lies a boundary beyond which light itself cannot return the event horizon. It is not a surface in the conventional sense, not a wall or a solid edge, but a limit in space-time defined by gravity so strong that escape is impossible. Once matter or radiation crosses that boundary, it is lost to the visible universe forever. Around this frontier, every physical quantity we can measure reaches extremes. Time slows to a crawl, relative to distant observers, space curves inward, and the familiar separation between past and future begins to dissolve. The event horizon is both the end of observation and the beginning of speculation, the threshold that transforms knowledge into inference. For a black hole of this magnitude, the horizon spans a region larger than the orbit of Neptune around the Sun, yet from its distance of 11 billion light-years, that immense scale collapses into invisibility, subtending an angle too small for any telescope to resolve. Still, its presence can be traced through the behavior of the matter around it. The inner edge of the accretion disk marks the last stable orbit where gas can circle without plunging inward. Beyond that radius, particles spiral swiftly into darkness, their radiation fading as gravitational redshift drains their energy. The light emitted just before disappearance carries the imprint of this boundary lines, stretched, blurred, and softened by gravity's pull. Through those distortions, astronomers glimpse the outline of the horizon even without seeing it directly. The concept of the event horizon arises naturally from general relativity. In Einstein's description, mass and energy shape the geometry of space and time. When enough matter is compressed into a small volume, the curvature becomes so steep that all paths point inward. The boundary where the escape velocity equals the speed of light defines the horizon. Inside it, space and time exchange roles. All possible directions lead toward the singularity, the core where density becomes infinite and known physics breaks down. To an outside observer, nothing that crosses the horizon can send information back. The black hole therefore conceals its interior, completely offering only indirect evidence of what occurs within. The horizon also determines the black hole's temperature and entropy concepts, first recognized when physics merged quantum theory with relativity. Although no light escapes quantum fluctuations near the boundary, produce tiny amounts of radiation, a phenomenon known as Hawking radiation. For supermassive black holes, this effect is negligible, far too weak to detect, but its theoretical existence links gravity, quantum mechanics, and thermodynamics in a single framework. It implies that even an event horizon possesses entropy, a measure of the information hidden within. For the colossal black hole powering this quasar, that entropy would exceed any other known in the universe, representing an unimaginable number of microscopic states confined behind the veil of gravity. The event horizon is not static. As the black hole accretes matter, the boundary expands its circumference, growing in proportion to mass. Each infalling particle adds to the curvature of space-time, enlarging the region from which light cannot escape. In the early universe, when fuel was abundant, this process occurred rapidly, allowing the black hole to reach its enormous size within a few 100 million years. During that time, the horizon would have grown by billions of kilometers, consuming gas dust and entire stars that wandered too close. In its current distant state, we see it as it once was already vast, yet still surrounded by inflowing material that fed its growth. The balance between this invisible expansion and the outward radiation from the disk defines the lifetime of the quasar. To imagine the horizon is to picture stillness amid violence. Everything around it moves at tremendous speed, yet the boundary itself remains silent, a one-way threshold indifferent to the turmoil outside. Matter approaching it appears to slow as time dilation stretches its motion, asymptotically freezing at the edge when viewed from afar. In reality, the material crosses in a fraction of a second, from its own perspective vanishing from the universe's record. The photons it emits just before crossing are redshifted to infinity, fading into the cosmic background. What remains observable is the thin shell of radiation hovering above the brink, the last visible whisper of light before it succumbs to gravity's silence. Around this region, space-time itself is dragged into rotation by the spinning black hole, an effect known as frame dragging. It means that nothing can remain still. Even light must move around the black hole in the direction of its spin. The boundary separating this region from the rest of space is called the ergosphere. Within it, energy can be extracted through interactions between particles and fields, a process that may power the quasar's jets. The horizon lies inside the ergosphere, marking the absolute limit where even light is bound to the singularity. These nested regions form a complex geometry that links rotation energy and gravity in one elegant but unforgiving design. Observations of nearby black holes, such as those imaged by the Event Horizon Telescope, have confirmed these predictions. The shadow they reveal, a dark circle surrounded by a ring of light, matches the shapes predicted by relativity. For the distant quasar, direct imaging remains impossible, but the same physical principles apply. Its horizon would cast a shadow tens of billions of kilometers across, yet dwarfed by the scale of its host galaxy. The light around it would bend and orbit, forming a glowing ring that, if seen, would shimmer with redshifted energy from matter on the edge of disappearance. That image, unreachable yet inevitable, defines the ultimate boundary between the known and the unknown. The interior of the horizon remains inaccessible, but its influence reaches far outward. The gravitational potential it creates shapes the orbits of gas and stars across the galaxy, binding the entire system together. Even regions millions of light years away respond to its mass, their motion governed by the unseen center. In this sense, the event horizon, though invisible, organizes the structure of the cosmos around it. It is the anchor of the galaxy's dynamics, the silent heart that defines both its stability and its evolution. Philosophically, the horizon marks a boundary between observation and imagination. Everything science can measure ends at this edge. Everything beyond becomes a domain of theory. Yet that limitation is not a failure, but a triumph of understanding. To identify the exact point where physics ceases to describe reality is to grasp the reach of human knowledge. The existence of an event horizon predicted by mathematics and confirmed by observation stands as one of the most profound discoveries in modern science. It demonstrates that the universe contains absolute boundaries, regions where information, energy, and time themselves converge into unknowable unity. Light leaving the vicinity of the horizon begins a journey of billions of years across expanding space. Each photon that escapes carries the signature of the gravitational well from which it came, stretched in wavelength but intact in meaning. When that light arrives at Earth and enters a telescope, it completes a path from the threshold of timelessness to the realm of human comprehension. The event horizon, invisible yet real, thus connects the most distant extremes of the cosmos to the smallest instruments of observation. It is both the end of matter's fall and the beginning of our understanding, a silent boundary written into the fabric of space, marking where gravity rules without limit and where the universe keeps its deepest secrets. Beyond the event horizon lies the region where direct observation ends and theory alone can follow. This is the domain of the black hole's interior, a place defined not by what can be seen, but by what physics can describe. The mathematics of general relativity predicts that inside the horizon space and time trade roles. The radial direction, once describing distance, becomes a path inevitably leading toward the singularity, while time itself becomes as constrained as space once was. No signal, no matter, and no light can reverse direction. The journey inward is not motion through space, but a progression through geometry ending at a point where density and curvature become infinite. It is the most extreme solution of Einstein's equations, and though it cannot be directly verified, the consistency of observations outside the horizon leaves little doubt that something very close to this mathematical prediction exists. The singularity at the core of a black hole represents a breakdown of classical physics. In this point-like region, all known forces converge, and the fabric of space-time ceases to behave smoothly. The equations that describe gravity elsewhere no longer yield finite answers. Such infinities are a sign not of mystery for its own sake, but of incompleteness, a place where general relativity must give way to a deeper theory that unites it with quantum mechanics. That theory, often referred to as quantum gravity, remains one of the greatest goals of modern science. While the external behavior of black holes has been confirmed with exquisite precision, what occurs inside the horizon remains an open question. The inner model is thus an exercise in inference, built upon the laws that govern what can still be measured. The simplest model assumes that the singularity exists as a true point of infinite density, where all matter falling inward is compressed beyond any physical limit. Time for an infalling observer would end there in a finite interval, though for the external universe that event would never be seen. But quantum theory, which forbids absolute singularities, suggests that other possibilities may exist. Some models propose that matter collapses only to a region of extremely high but finite density, held by quantum pressure or other, as yet unknown effects. Others envision a transition to a new phase of space-time, perhaps linking to another region of the universe. These ideas remain speculative, supported by mathematical consistency, rather than empirical data, but they reveal how deeply black holes challenge our understanding of nature. The interior is also a stage for the interplay between entropy and information. The concept of black hole entropy, introduced in the 20th century, treats the event horizon as a measure of hidden information. Each unit of area on the horizon corresponds to a quantum of entropy, implying that everything crossing the boundary contributes to the total information content of the black hole. Yet this raises the paradox of whether information is truly lost. Quantum mechanics forbids complete loss of information, while classical gravity demands that nothing escapes. Reconciling these principles has led to the concept of the holographic universe, in which all information about matter inside the black hole is encoded on its surface, much as a three-dimensional image can be represented on a two-dimensional film. This holographic principle provides one of the most intriguing bridges between relativity and quantum theory. For a quasar's black hole of such enormous mass, these quantum effects are vanishingly small compared with its classical behavior, but their conceptual importance remains. The horizon may act as a recording surface, where each infalling particle leaves an imprint in the pattern of space-time itself. Over incomprehensible spans of time, as the black hole slowly emits Hawking radiation, this information could in principle be released back into the universe, preserving the total balance of cause and effect. The process is unimaginably slow for supermassive black holes, far longer than the current age of the cosmos, but it represents a profound theoretical reconciliation that even the darkest objects may not be entirely silent to physics. The inner structure of a rotating black hole adds further complexity. The equations of relativity predict that rotation flattens the singularity into a ring rather than a point, and that inside the horizon, new regions of spacetime may open connected by mathematical bridges known as wormholes. These connections are unstable in classical theory and would collapse instantly under any disturbance, but their existence in the equations suggests that gravity may permit geometries far richer than the simple notion of collapse. Some speculative models explore whether quantum effects could stabilize such bridges, creating transient links between distant parts of the universe. These ideas remain beyond testability, yet they remind us that even established physics leaves room for imagination, guided by law. The inner model also considers the fate of matter that crosses the horizon. From the outside, it seems to freeze at the edge, redshifted until invisible. From the viewpoint of the matter itself, however, the fall is swift and uneventful. It experiences increasing gravitational gradients or tidal forces that stretch it along the direction of motion and compress it across an effect known as spaghettification. Near the singularity, these forces become overwhelming, tearing apart every structure down to the level of atoms. In a rotating black hole, this process may be moderated by frame dragging, allowing particles to spiral inward along complex paths, but the end result remains the same. Matter is reduced to fundamental energy within the geometry of the singularity. The distinction between matter and space becomes meaningless, replaced by curvature alone. To reconcile these extremes, physicists explore models that combine quantum field theory with curved space-time. Some propose that the core of a black hole may undergo a phase transition into a new form of matter, or even a new region of the universe. Others imagine that quantum fluctuations at the Planck scale prevent complete collapse, replacing the singularity with a finite but extreme structure, sometimes called a Planck star. In such a scenario, information might one day re-emerge in a burst of radiation, turning the endpoint of collapse into a beginning. Though these ideas remain hypothetical, they embody the spirit of inquiry, that black holes inspire the pursuit of knowledge where direct experiment is impossible, guided by the coherence of mathematics and the evidence of light. For the great quasar's black hole, the inner model is necessarily abstract, yet its outer behavior provides constraints. The stability of the accretion disk, the symmetry of the jets, and the steady luminosity all indicate a rotating, well-ordered system consistent with the Kerr solution of general relativity. In that model, the black hole's spin determines both its shape and the structure of space around it. The singularity, if it exists as a ring, would be surrounded by nested horizons separating different regimes of motion. These features may remain forever unseen, but they shape every photon that escapes from the surrounding disk. Through their influence, the unseen interior leaves a visible mark on the cosmos. Ultimately, the inner model represents the limit of what physics can presently describe. It is a map drawn at the edge of understanding, where observation meets the boundaries of mathematics. The equations predict regions where curvature becomes infinite, where the distinction between cause and effect dissolves, and where the flow of time ceases to have meaning. Yet those same equations, when tested against every observation outside the horizon, remain flawlessly accurate. The success of general relativity in predicting the behavior of quasars, gravitational lenses, and black hole mergers gives confidence that even unseen, the core of this quasar behaves according to those laws. The inner model therefore stands as both a mystery and a triumph, a theoretical window onto a place forever hidden, whose presence is confirmed not by sight, but by the harmony of light and gravity that surrounds it. In that harmony, the invisible interior becomes a symbol of the balance between knowledge and wonder, reminding us that even the most complete theories must coexist with the infinite depths of what is yet unknown. The light that left the quasar's core more than 11 billion years ago has travelled through nearly the entire history of the universe to reach us. Along the way, it has passed through expanding space, stretched and cooled by the growth of cosmic distance. Each photon has been scattered, absorbed, and re-emitted countless times before finally entering a telescope on Earth. What we observe today is not simply the present state of the object, but a fossil image from a time when the cosmos was less than a fifth of its current age. Through that light, the early universe speaks across vast epochs, carrying information about both its origin and its evolution. The photons we detect today began their journey as radiation from the accretion disk, the corona and the jets surrounding the colossal black hole. They escaped the gravity of the central engine, passed through the broad line region, filtered through the circumgalactic medium, and then entered intergalactic space. There they encountered the hydrogen fog that filled the young cosmos. Some were absorbed, others scattered, but the faint remainder continued crossing billions of light years before reaching detectors sensitive enough to capture their whispers. Each wavelength tells a part of the story. The ultraviolet traces the disk's heat, the optical marks the emission lines of surrounding gas, and the radio waves carry the memory of the jets that once spanned intergalactic distances. Together, they form a complete narrative of light, recording a moment that still shines, even as its source has long since changed. As the universe expands, every photon's wavelength lengthens. What began as ultraviolet becomes visible. What began as visible becomes infrared. This stretching of light, known as cosmological redshift, transforms not only color but energy. The glow of the quasar we see today is dimmer and redder than it was when it first emerged, yet it retains the structure of its original spectrum. By measuring that shift, astronomers determine the distance and age of the source. For this quasar, the redshift of about 2.2 corresponds to a time when galaxies were still assembling, when star formation was at its peak, and when the first large-scale structures were taking shape. The light that has arrived now therefore carries the record of a younger cosmos, allowing us to see not just a black hole, but an era of creation and transformation. the intergalactic medium through which this light has passed is not empty. Clouds of gas filaments of hydrogen and thin traces of heavier elements absorb specific wavelengths, leaving a forest of dark lines in the quasar's spectrum. This pattern, known as the Lyman alpha forest, serves as a map of the universe's structure along the line of sight. Each absorption line marks a separate concentration of gas at a different distance, revealing how matter is distributed on scales of millions of light years. In this way, the quasar acts as a cosmic beacon, illuminating the invisible architecture of the cosmos. The same photons that record the behavior of the black hole also chart the growth of galaxies, the enrichment of intergalactic gas, and the transition of the universe from opaque to transparent. Over time, these photons have been stretched not only by expansion, but also by the curvature of space. Gravity from intervening galaxies bends their paths, slightly producing small distortions known as gravitational lensing. In some cases, this bending can magnify the quasar's image or even create multiple copies of it, separated by arc-seconds on the sky. Such lensing allows astronomers to study both the foreground structures that cause it and the background source it magnifies. Although this particular quasar is not known to be strongly lensed, its light has still experienced countless minor deflections along the way. Each bend is a small testimony to the presence of unseen mass dark matter distributed throughout the cosmic web that shapes the geometry of the universe itself. The arrival of these photons at Earth marks the end of an extraordinary journey. After traveling more than 10 billion years, they enter the atmosphere where air molecules scatter some wavelengths and absorb others. The faintest ones pass through strike mirrors and sensors and are converted into electrical signals. Those signals become data arrays of numbers, graphs, and images that scientists interpret with models and equations. Through that chain of transformations, light from one of the most distant and massive black holes ever known is translated into human understanding. The quasar's glow, once the output of a furious accretion disk, now exists as patterns on screens and pages, its energy reborn as knowledge. Yet even as this light reaches us, the quasar itself may have changed beyond recognition. In the billions of years since the photons left, the supply of gas around the black hole may have dwindled. The once blinding nucleus could have faded into a quiet elliptical galaxy, its central engine dormant. The jets that once spanned millions of light years may have dispersed, and the host may now drift in a tranquil cluster, surrounded by the relics of its own brilliance. The image we see is thus a window, not to the present, but to the past, a record of a moment that no longer exists. In observing it, we are not watching a living event, but reading the preserved light of ancient history. Still, that ancient light continues to inform us about the mechanisms that shape galaxies even today. The same physics that governed the quasar's core governs the supermassive black holes at the centers of nearby galaxies. The accretion disks, broadline regions, and coronae observed across the cosmos follow the same principles scaled by mass and luminosity. In this way, each quasar serves as both time capsule and template, showing how black holes grow, radiate, and interact with their environments. The light that began its journey before Earth existed now helps explain the structures we see in the modern universe. The energy emitted by the quasar also contributes to the cosmic background that fills all of space. Over billions of years, the combined radiation of countless quasars has created a diffuse glow known as the X-ray and ultraviolet backgrounds. This light influences the temperature and ionization of intergalactic gas, shaping the conditions under which new galaxies form. Even after individual quasars fade, their accumulated energy continues to sculpt the cosmos. The quasar's light, in other words, becomes part of the environment that will nurture future generations of stars. In human terms, the scale of these events defies comprehension. The photons detected by telescopes tonight began their journey when the Milky Way was still forming. They traveled through epochs when galaxies merged, stars were born and died, and heavy elements filled the interstellar medium. During that time, entire civilizations could have risen and vanished in countless worlds without affecting the path of a single ray of light. The arrival of those photons in our detectors is therefore an act of cosmic patience, a process that spans nearly the entire history of the universe, linking the distant past to the living present. The study of that light closes the circle of cosmic inquiry. From the outer structure of the host galaxy to the inner edge of the event horizon, each layer of the quasar contributes to the message carried by its radiation. When combined, these signals form a coherent story of gravity and energy of creation and transformation, written in wavelengths that stretch across the universe. The light that has finally reached us is more than evidence of a distant black hole. It is a testament to continuity, to the persistence of physical law across unimaginable scales of time and space. Each photon embodies the same principles that govern atoms and galaxies alike, and in following its path, we trace the unity of the cosmos itself. As the last faint quasar light fades into the background sky, what remains is the realization that the universe is a single unbroken sequence of cause and effect. The radiation that left the accretion disk billions of years ago now illuminates our instruments, connecting events separated by both time and immensity. The journey of that light is the journey of understanding itself, an unending passage from darkness into awareness. Though the quasar may now rest, its light endures, carrying the memory of its existence through the expanding cosmos, a record of brilliance preserved in motion, forever crossing the quiet between galaxies and ages.